I'm going to talk about some recent work that I worked on with two colleagues. I should mention their names. So Asaf Cohen, uh, most of you know as well, um, and April Mellis, who was our joint PhD student. She now works for Johns Hopkins University, uh, Applied Physics Lab. Applied Physics Lab. So this is something new for me, decentralized finance currency exchanges and their analysis. But I'm an expert on mean field games, and I thought that when we were looking into these markets, that actually mean field analysis would be appropriate for these kind of markets. And I'm trying to convince you that this is the case. I was convinced myself. So let me start. So let me give you a brief overview because this is something new to many people. So this basically decentralized exchanges are codes deployed on a blockchain, and there are no central entities that execute trades. So it usually an exchange facilitates exchanges between crypto tokens. So for example, one of the most prominent ones are Ethereum versus USDC, USD stablecoin. And there are these functions built into the stacks, and they are called automated market makers. And they take place of what traditionally would actually match the buy and sell orders. So, for example, there are these other venues you can trade in, so Binance and Coinbase. But you can go to something like a Uniswap, and that would be decentralized as opposed to centralized. So these exchanges exist to serve swappers, right? So there's people who wish to exchange token A for token B or token B for token A. There are each exchange you can in each of these pools. So these exchanges are called pools. In each of these exchanges, you can swap A for B or B for A. And of course, others have to come in and provide these tokens that are needed. These are the liquidity providers. They provide the reserves to the pool. And of course, they don't do this function for free. They do this in return for some transaction fees. So here is how the thing looks like. So there is a swapper, and he wants to get out some tokens of B, right? So there are reserves in the pool, a pool. So there is a pool, right? There are reserves of B and A, both of them exist in this pool. And swapper wants to take out some of these. He needs for some reason, so for some personal reasons, 5 token Bs in this example, and the AMM determines how many tokens he should deposit in the pool, how many tokens of A he should deposit in the pool for these 5 that he took out, and in addition to this, he is also depositing a fee. And as I said, there are multiple pools, right? And we'll talk about this, right? So this is not there. There are several there are several tokens, right? So there are 1,000 tokens in Uniswap. There is one of these venues is Uniswap, and Uniswap supports exchanges between 1,000 tokens, and there are more than 2,000 pools in Uniswap. And so to do the analysis, we picked one of these. And this is, as I said, the most popular one is the USDC, the USD stablecoin, and Ethereum. And this has like there are several fee. So for each fee, rate, there is a different pool, right? So we picked the one with the most customers. So we have 5 basis points fee for this, the one that we picked. And when you go to Uniswap, you can go online and basically the page looks like the following, right? So it is the USDC Ethereum pool, and here's the fee rate, right? And you see there are two functions. You can add liquidity, so you can become a liquidity provider, or you can swap. So you can also change your fees and go to a different pool. And you can see that there are a certain number of tokens that are available in the pool. So there's 130 million USDC tokens, and this is basically $130 million. And then 16,000 Ethereum tokens. And the total value locked is reported here. It's 191 million. And then you can see the volume that was traded in the last 24 hours and the fees that were collected by liquidity providers in the last 24 hours. So this is what the screen you see. And then you also see the current exchange rate, right? So this is the current exchange rate. One Ethereum is trading for 37.40 at this pool currently. So let's look at liquidities because we are going to take the liquidity provider's position. So liquidity basically means how many token reserves you have in the pool so that you can facilitate swaps, and the higher liquidity means that larger swaps can be accommodated with less volatility, so not much price change. So this is ideal situation. So Uniswap, I'm going to look at Uniswap V3. There is now Uniswap V4, but the most common one in the pool that is used in the pools is Uniswap V3 by a lot. Like it's about 55, 53 or 55 last time I checked. Percent of the pools are run by Uniswap V3. So this is concentrated liquidity. So that name is given to it in contrast to Uniswap V2. Because in Uniswap V3, you somehow can specify the ticks that you want to trade in. So each tick here, for example, tick I, is associated with a price interval, PI to PI plus 1. And so Uniswap V3 divides the pool into ticks, and you don't have to contribute liquidity to every tick, but you can actually concentrate your liquidity provision to certain ticks, right? So I'm going to enumerate, ticks will be important for us, and I'm going to enumerate them by I, and there will be D ticks in this talk. So this, so if you look at tick I, we'll say that tick I has liquidity Li, right, and this inequality is satisfied between the reserves of token A and B at that tick, right? So Li is our liquidity. This is what we call liquidity. And at that tick, this is the number of B reserves. This is the B reserves, and this is the A reserves at tick I. This is called a virtual reserve here, and this is basically how the mechanism operates. If you look at the second equation, so for example, if I want to take out as a swapper Y tokens, then the question is how many B tokens should I put in? That's determined by this equality here. So there are D ticks, if you remember, and I'm going to call this vector L. So this is the vector of Li's. We will call this the liquidity distribution. All right, so let's look at this in a graph, or in a couple of graphs rather. So the liquidity distribution will look like this, right? So here is at the bottom is the exchange rate. That's B over A. And on the left-hand side, we see the liquidity. So this tells me how liquid each tick is. You can look at this in terms of the reserves. So token A reserves are to the right. Token B reserves are to the left. So token A is like Ethereum, right? And token B is like USDC. But I am just I have my arbitrary A and B here, but that's what I have in mind when I'm talking about these. And what you notice is that at the current tick, so I'm going to enumerate them. Remember, so the ticks. So this is the first tick, second tick, third tick, fourth tick, fifth tick, and sixth tick. So third tick is the current tick or the active tick, right? This is the third tick. And at the active tick, both my reserves contain both A tokens and B tokens. But the inactive ticks, to the right, there are only A tokens, and to the left, there are only B tokens. That's how the pool looks like. Right? So then in this functional equality, right, to the left, so A and B are both present only at the active tick. So we can call that I star. So BI star plus LI star times PI star multiplied with AI star, right? Plus Li divided by square root of Pi star plus 1 is equal to Li star squared. But otherwise, to the right of the active tick, this is 0, so you can calculate AI. And to the left, this is 0, you can calculate the BI reserves, right? So it will be proportional. So BI will be Li times square root of Pi plus 1, Pi plus 1 minus P square root of Pi, right? And you can also solve for AIs, right? So these are all quantities that the AMM determines. So let's look at it. So I give you, when a liquidity distribution is given, as on the left-hand side here, the right-hand side, right? So the liquidity is these vectors here, and I plotted them, right? And on the right-hand side, what you see is the true exchange rate. So how the exchange happens. So AMM calculates, for example, when the swapper comes in and wants 7.6 tokens of A, the AMM calculates how many tokens of B. You can also do the calculation, but there is a nice explicit formula that you can obtain to actually draw this concave curve. That it requires the investor to deposit 13.5 of tokens of B, right? So this is the calculation, and I'm going to refer to this function phi later on. So phi of x, right? X is the swap size, and L is the liquidity vector. Given this, we can actually draw this curve. Given the liquidity distribution, I have a corresponding curve that the AMM uses. So let's look at how swapping works. So we have a liquidity distribution on the left, and this corresponds to the right? So because we trade in terms of tokens. So they are in one-to-one correspondence there. So there's token A reserves and token B reserves. So we want to swap, right? So there's the current instantaneous rate is 1.67, right? So it's in this is the active tick right now. And let's say that a swapper comes in and wants this many tokens of A, right? So what happens is that he eats into the A reserves at that active tick, and then adds in that active tick B reserves, right? So given the formula. Well, it might be that he wants some other the swapper maybe wanted more tokens, right? So it could actually eat up the all the tokens in the current deck. It could be actually moving to the right. So what happens is that so if somebody comes in and requests more tokens than we have in the this current deck, right? So it eats up into this, adds token reserves to that same tick, but now it starts eating up into the next tick, and he has to add now more B reserves, and this action moves the active tick to the right, right? So active tick is the only one that has both A and B reserves. So when this happens, when the swapper comes up with a huge demand for A, it moves the prices, right? All right. So this is the mechanics of it. Now we want to look at the problem of liquidity providers, if you remember. So the liquidity provider is going to come in, right? And is going to tell us how wide he will support the pool. Like, so he'll tell us actually the pair of ticks, I and J, right? Such that he's going to spread his liquidity over this interval, right? So this is how it works. So you select this rates, PI, PJ, exchange rates. And then the liquidity provider has a certain amount of capital that he wants to contribute, right? And he's going to distribute this among the ticks, this capital. So how does the AMM let you do this? You basically, it says you need to provide equal liquidity to all the ticks that you provide into. So here PI is the, so here's a tick, right? So PI, right? And then here's PJ, right? So we are contributing actively from I all the way up to J minus 1, but not the J one. So this is my notation. So what we want is the liquidity provider to contribute equally to all these ticks, but contributing, right? So I'll explain this mechanism a little bit better later on. Their liquidity providers has to take into account the current pool exchange rate. And also there is a centralized exchange, right? So centralized exchange, you could consider it more liquid, right? It can accommodate bigger trades without price changes. So there is that also. We call that the market exchange rate, M for market. So there is that, right? So there is somehow these trades create some arbitrage, might create some arbitrage opportunities because the price is deviating from the market exchange, and liquidity provider has to take this into account. Be careful about this. Anyway, we'll come to that. And here is how liquidity provision looks like. So if you had clicked on the previous screen where it said liquidity provision, right? Then you would see a screen like this. So you would select a price range, right? So this is basically choosing this IJ. So where you're going to contribute your liquidity. And then you would enter, for example, how many Ethereums you will contribute, and it will tell you how many USDCs you have to contribute as well. So you have to contribute both. And then it tells you the total capital that you owe, right? I mean, it doesn't have to tell you because you can compute it. Given the current market exchange rate, you can say this actually will be costing me $56,000. So this, you give one of them, the AMM computes the other. All right. So let's look at how adding liquidity looks like. So there is a liquidity distribution again. There are the token A and B reserves as before, right? So now a liquidity provider came in and he has 2.887 token B worth of wealth, right? And he chose to contribute to these ticks, right? 2, 3, and 4. And because he has 2.87 worth, capital of token B, the AMM calculated that this corresponds to contributing 10 liquidity units, and that actually corresponds. And then if you look at it in terms of reserves, of course, that's all over the place, right? So they're not. This is uniform, but the token contribution is not, right? So the token contributions, smaller amount of A here, a little bit larger here, right? Smaller amount of B and a little bit larger amount of B there to the left, right? So it ends up that the liquidity provider provided token B's to the left side, token A to the right side, and both token A and B to the active tick. All right, so let's come to our problem. So this is the setup, but it's complicated. So not many people know about the dynamics of this. So I have to explain all that. So now I want to sort of motivate our own problem. So we look at what's the motivation of liquidity providers? Well, they want to earn fees, right? So let's say that we are at this pool with 5 basis points fee, and there are 6 liquidity providers providing to this active tick, right? There are maybe more liquidity providers, but the active tick has a contribution from 6. And let's say that there's a swap size of $120,000, right? So with a 5%, 5 basis points fee, this corresponds to $60. So this trade is $60. So each liquidity provider would get proportional to the amount that they provided, since they are, as you can see from the coloring, they are providing equal liquidity. Then their share will be a sixth of everything, so it will be $10, right? So that so far so good. But what if one of them decides to double its contribution? Well, then we look at the shares that they get. The one that doubles his contribution will get $17. So he moves up from 10 to 17, whereas the others now are decreasing in what they receive, right? So they went down from 8 to down from 10 to 8.57. So then they wake up and say, hey, okay, this guy is cheating us. Let's also double. We all double. Then it goes back to the original place where we are all getting 10. So now right. So in other words, the story is that they are interacting, right? So they have interaction, and they're interacting through their actions, right? So there is an interaction between the liquidity providers. So they have to take each other into account. What does that mean? It's a game between the liquidity providers, because the fee is distributed proportional to what they contribute, and you can change that, and you can increase your share of fees. So there is an optimization problem the liquidity provider does, right? So because after all, why are you providing liquidity? You would like to make some profit. So there is an optimization problem they are interested in. And there is some randomness in the pool. So we have to model this, but plus actions of other players that affect you, have to model that. And we need to see how the actions of the other players affect the liquidity provider's decision. All right, so let me set up the problem a bit more in details. So we're going to take, so of course, one of the decisions to make is how long you will leave your liquidity in the pool. And I'm going to decide, I'm going to look at so the problem is basically liquidity providers 1 day. Okay, so I'm going to take 24 hours. And this is 7,200 blocks. So meaning so there are blocks here, blocks of trade. So the trades are done every 12 seconds. Right? and I'm going to take 7,200 blocks, and this is our time horizon. I'm going to set it this way. I'm going to simplify my life because I'm doing like the basic first analysis here. So if this is looking good, maybe I can make it much more complicated. But I'm going to fix the time horizon for everybody to be 24 hours. Of course, everybody has different amount of capital. Everybody has different amount of risk aversion. Take this into account. There's also the market rate that changes. So I have to take this into account. And the pool rate also changes, right? Because there are swappers that come to the pool, and some swappers might come to the pool because there's an arbitrage, right? So if the price level is too different, it might be that I attract swappers for this reason, for this very reason. Swappers might want to swap just for some personal reasons. Maybe they want to buy something, and that requires that particular currency. But it might also be that they are coming into the market to take advantage of the arbitrage. So we have to also model that, right? So our liquidity providers have a horizon, and they will model the swapper behavior. So okay, so we will represent, so some notation is necessary now. So we will represent the capital by K. And here, right, K is our capital. And risk aversion parameter by lambda. That's the risk aversion parameter. And then they will have a market outlook also. We allow these liquidity providers to have a market outlook, right? So I'm going to represent by delta. So an outlook is about like where the exchange prices are going to go to, right? So if it will be +1, 0, or -1. So 0 is no change, +1 is positive change, and -1 is negative change. So they have an outlook. And I also, as I said, yeah, so this is the change. And then I'm going to denote this individual characteristics by kappa lambda delta as this triplet. Okay. So we are going to estimate the swapper behavior, right? So as a liquidity provider, we have the data. This is the nice thing about these exchanges. You can actually pull everybody's trades, by wallet ID from Etherscan, and you can analyze it, right? So this is easy to do. You can analyze it and write a code and look at how the swappers behave. So the swappers potentially are motivated by the arbitrage level, but not necessarily so, right? So we want to, but we want to model this, right? So here we get here is how we model this one. We're going to say, okay, as a swapper is going to come or not, depending on the arbitrage level. So the difference of PT star minus M star, and you plug this into a function, and then this is the rate of your Bernoulli coin flips, whether a swapper arrives or not. Right. So here we did a calibration to the data, and we put a smooth function rho, which I can give you what it is explicitly, but this is not too necessary. And then also the size and the direction of the swap, you can plot this. So you can plot C versus the difference, right? And you can see you can try to look at the joint distribution of them, right? So you can actually look at the whole joint density of this swap size and the price difference from the data, right? This is empirical. And then you can, fit some some density estimates you can obtain. So that's what we're going to do. What we observed is that there is actually some correlation, but the difference does not explain the arbitrage level does not explain why there are the magnitude of swaps complete it only has a small explanation power. Let's put it this way. You do see a correlation, negative correlation, but it doesn't explain the entire swapper behavior. So therefore, we just calibrate it from the data. All right, so let's look at our swappers. So the capital endowments, right? So I'm going to take this as a discrete variable. So we do like some cluster analysis and look at the liquidity provider wealth distribution, and as there is, and we see that there are small trades which are about $2,000. There are larger trades about $30,000-$40,000, and then bigger trades about $1.5 to $2 million, right? So we will after an analysis of the data, we see that this is the level of capital endowment we take, and then we can also look at the risk aversion parameter. So we'll take this to be between 0 and 5. And this is basically, you look at our cumulative profit over this capital T time horizon, right? This is, remember this number of the 7,200 number of blocks. And we look at the expected value and variance of this profit, and we do a mean variance type of analysis for the liquidity providers. The liquidity providers also have a belief, as I said, about the market trends. So whether the Ethereum price will increase or decrease, they form a belief, and we allow them to form 3 beliefs. So either the price doesn't change, price increases, price decreases, and we model it like this. So MT star is equal to MT star N star at T minus 1 times a log exponential Brownian motion. All right. So each liquidity provider, right, when you're there, so the profit function, I mean, I can write as profit function, but it doesn't actually give you too much. But the profit function depends on, of course, my choices, I and J, Xi, the swap, right, my characteristic, theta, the characteristic, how much money I have, my risk aversion parameter, and the directional belief, and the liquidity of the market, right? So there is this L, that's the liquidity. That's what I'm trying to optimize by how well, whether I'm going to spread out thinly, right, or not, right? I could actually either thinly spread it out, or I can cluster it, my liquidity, right? I can skew it, and I also can skew it. So I could provide more in this direction or more in that direction, liquidity. So this is something that I have to decide on. So let's say that so let's look at actually where the randomness comes from, right? So I have this expected value and variance. So what measure am I taking an expected value with respect to? Well, it is the swappers, of course, bringing the randomness, right? So that's why I'm highlighting C here. So that's the random component, right? To given L. So I'm given the liquidity distribution. The swapper's behavior is what I need to take into account when I'm calculating, making my optimization decisions. So Xi, this Xi variable at time t depends on, of course, the difference between the prices, the exchange price versus the pool price, right? And there is a random evolution, as I said, geometric Brownian motion for this guy. And obviously, the price is also random because Xi is going to be random. It's a random evolution. I know the initial prices, of course, when I start this, but I'm letting my horizon is capital T. I'm going to choose and set for a capital T units of time. And that's basically the model, right? So that's what the problem that I have to solve. Now but the problem is that as we just discussed in the pictures, right? The liquidity distribution is not fixed, right? Because it's not like I come into if I went to an exchange, of course, that you could assume to be fixed, perhaps. But you come to this pool, I do affect the liquidity distribution, right? So and the others effect on the liquidity distribution affects me, etc. So I have to think about this a bit more deeply. I can't assume it as given. So we basically have a game here, right? Because the interaction, as I said, is through this L. There is a game. It's not just like an optimization problem, but you have to do a game. So the thing is, when you look at this Uniswap data, there are hundreds of liquidity providers. So then, well, this looks like a large player game. And the players really are symmetric given all their characteristics, right? Kappa, lambda, delta. So it really looks like a mean field game. Like it is a mean field competition between these two, between the liquidity providers. So I will have these theta. I'm going to call this the characteristic to shorten it with theta, and theta has a distribution, and I'm going to choose a support of theta, right, like this, as I've already indicated, right, and a representative player, given the liquidity distribution, tries to maximize the value function that we described, right? Given his characteristic theta. So given his characteristic theta, he's trying to maximize this the value that we discussed already, and then we update given this liquidity provider's actions, right? So everybody's action, we can update. There's an update function. So you check whether this is a bin from 1 to D, and you check whether this bin falls into the characteristic of the player's theta's the range, and then you add their liquidity, right? And integrate with respect to the whole number of the whole population, right? So this is the liquidity update given the players react to the liquidity. So first players react to the liquidity, and then we update, right, the liquidity given the player's reaction, right? Well, of course, obviously, a mean field game is basically the equilibrium point of this. So we are basically trying to find a pair J star L star such that J star is the best response to L star, and L star is formed by this J star with the liquidity map that we just talked about here, right? So we basically can talk of a mean field game here. Okay, so all right. I think it's convincing that this is a mean field game. Great. But can I represent the observed liquidity distribution as a mean field game? Can I empirically do this? And can I use this to make some predictions? So here is the observed liquidity distribution. So you go to the data, right, on a particular day. This is November 29, 2023, so about 2 years ago. Here is how it looked like at a certain point in time, the liquidity distribution and the token A and B reserves, all right? And then what we do is we calibrate the theta. So we calibrate theta, right? And then look at its mean, so look at what it then produces, what the calibration produces. The mean field of the calibration. So given theta, I can find a mean field equilibrium. So I calibrate the theta, and I look at the picture it produces. It does a decent job. So it's not exactly the same because it didn't capture these spikes, but it does more or less look the same, and you can actually measure it in terms of the Wasserstein-1 distance, because these are like this is like an unnormalized Wasserstein distance, right? And it's very close because it basically it's because the Wasserstein Earth mover distance, right? So you have to just move four liquidity units one tick, then you get the second one from the first. So it's very close. And actually, as a comparison, when we did this exercise for n-player games, so we did actually look at n-player games and we calculated the same thing, and n was equal to 10. The problem was that the computation was becoming very expensive, and we calculated this Wasserstein distance. It was about 18, a little bit more than 18. So this actually is a huge reduction in terms of that. So the large player approximation seems to be working here. Of course, okay, so we can explain this data. All right, so but that's not okay. So what, right? So moreover, what we can do is the following. So we simulate it. So I get the characteristics of the players, and then I simulate the data for a whole day without changing these characteristics. And then I look at the liquidity distribution at the end of the day, and I can compare it to the liquidity distribution at the end of the next day, the true liquidity distribution, and then look at the Wasserstein error, right? So, but I'm not changing the characteristics that I obtained for the players from November 29th. And I do this, and the picture looks like what we see here. And you can see, okay, it's not exactly the same picture, but it's awfully close. And the Wasserstein distance just increased a little bit to 4.43, right? So Wasserstein one error is, they are basically very close to each other. So it has some predictive power in that sense that it actually can predict the liquidity distribution for at least 1 hour. So you can keep calibrating this, and then you look at next ahead and maybe make some judgments based on that. And then we can also, of course, look at the simulated market rate, pool rate, and the market rate. So on the left-hand side, there's a simulated pool rate and the market rate on top of each other. On the right-hand side, there's a real pool rate and a market rate on top of each other for a period of time. Okay. And what we see is that they more or less overlap. I mean, of course, there's distinction on the left, right? The market and the pool rate, they more or less overlap. On the left side, they differ a little bit, but you sort of capture the gist of the movement. And the percentage error, maximum absolute percentage error, is about, is between the two functions is about 0.14%. Right, so it is a good explanation power. So the question is, okay, it's pretty good as a predictor. Can we make it better? Right? And we thought about adding MEV bots to do this. So MEV stands for maximal minor extractable value. So these guys basically they are able to see the so every 12 seconds there are transactions, right? So these bots are able to see what is in the mempool in this time, and then they can act accordingly. So basically, they know the swaps. They basically can observe the swaps, and then make a decision based on this, right? For the liquidity providers, this is a random process, but for these bots, they can come in and observe it, and then make a trade based on this, based on what they're seeing. Okay, so there are companies actually built around these, right? So you can actually contribute and contribute to these MEV bots and then take some profit off. Okay, so how then? So there are different types of bots, but most common one I should mention is the one that I'm going to talk about is just-in-time liquidity attack. Right, there are other types, but they have become over time because somehow the people have woke up to it, and they made some changes so that took care of some of these bot attacks. But just-in-time liquidity attack it increased actually the frequency of just-in-time liquidity attack. So people shifted to do this. So what does a just-in-time liquidity attack look like? So you can ether scan, so you can see these things. So as you can see, this is the wallet ID of this the same wallet ID of a bot. It minus sign, it means it leaves its pocket. Plus sign means it collects it. So it adds liquidity, this bot. As you can see, it adds quite a bit of Ethereum and USDCs, right, to the pool. And then there's a swap that happens. So somebody's trying to swap and get USDC, right? And then after the swap takes place, so the bot actually is responsible for most of the swap, right? If you do your addition well there, so paying attention that this is 10 to the 5 and this is 10 to the 7. It's much bigger than the swap, so it's really taking most of the swap at that time. And it basically wipes out everybody else's fees, right? So before the swapper, before the swapper came, everybody was aligned in this fashion. They sent their orders to be executed, and then suddenly a bot occurred, right? A bot came in, and the bot contributed a lot more. So it contributed 66%, for example, in this example, and took away $40 out of $60, right? And the others got a little bit of money. So again, a bot can see the swap, so then he positions himself. So it's the swaps, right? So he sees the swap, so he positions himself before and after, and then takes away the liquidity, right? So what could we do? Well, because it is the liquidity providers, it's like a contract problem, right? So the liquidity providers already decide for a period of time how, like their interval of liquidity, right? So they already have this liquidity distribution. They provide this, and then seeing this and then swaps, we do have an attack by the bot, right? The bot takes this liquidity L into consideration, right? And based on this, decides to attack, right? And the amount, and then there are some decision parameters that he's going to choose, right? So this is like a Stackelberg game or a contract problem, right? So the liquidity providers should collectively, so it's a mean field. So in other words, like it's like a mean field principles and a single agent kind of problem, right? So they sort of collectively have to decide on a decent liquidity distribution so that the bot does not take away as much as he could, right? So this is a Stackelberg game that we have to play, and the bot basically sees that there's no randomness in the bot's decision, right? So this is the swap size, so he sees it at a given time. Minus, this is the current exchange. So I'm converting everything into the one unit, right? This is the psi function that I had mentioned already. So if I have C tokens, how much money I'm going to of the other token I'm going to get, right? And we are counting everything in terms of one of the tokens. So that's why I'm multiplying this with M star. And this is the difference. So this is basically, there could be potentially profit from this swap, and the liquidity provided by the swap, bot is L, right? And then there so he gets some fees proportional to what he provides here. And then there are some gas fees here also, right? And then he will have to like decide whether he should attack or not, depending on whether this quantity is positive. And this is the quadratic optimization, quadratic problem here, basically. So if you write this out, it's a quadratic problem. That's not an optimization problem, so a quadratic problem. And you can find that if, for example, C is positive, this is going to be negative, this is going to be positive, right? So what you see is that he attacks only if the size is large enough. So because you could think of it as like if there could be signs of the C, right? So it could be negative or positive. So if C is positive, you will have 0 to C plus, right? And in this interval, he will not attack, and only if the swap size is large enough, it will attack. Right? So once he decides on these barriers, right, then we plug these back into the liquidity provider strategy, and then they have to choose the mean field liquidity to like the Stackelberg game, right? So they choose a contract, basically collectively they choose a contract for which the bot. So this is the bot strategy, but for which the bot does not make as much profit. So we do this, right? I mean, I'm not going to mention this here, but when we do this, we see that the liquidity providers make their interval smaller, so they condense their. So it's what you would expect, right? The liquidity providers don't spread out their orders anymore, but they try to accumulate it to the center. That's the best reaction, and then you can see that actually they don't lose as much. They still lose to the bots, but they don't lose as much if they do this. And from here also you can actually, because these are all explicitly calculatable, you can see, for example, that if the fee here increases, then the attack level decreases. If you gas fee, this is the fee that you provide to the miners, increases, then C plus increases. You can make this some analysis, and these are all actually these all analysis matches what is observed in the data. All right. So when we do this, okay, then when we calibrate, right, we do get we do get improved predictions. So again, we look at we calibrate and we run it for 24 hours. We see that we get increased correctness. Like, so for example, previously we had we ran what's calibrated for a whole day. Then the Wasserstein 1 error was 4.43. Now it is 3.38. So it improved actually the accuracy of our predictions, in fact, including the behavior of bots. And then we also do the simulations, and the simulations also look much better. Simulated pool rate now matches the market rate a little better than before. Right, so you can see improved efficiency on the mean absolute percentage error between these two functions, and that's it. If you would like to have a look at our paper, it's available at this link. You can scan and access the paper on SSRN. Thank you so much for your attention.
Thank you, Erhan. Very nice talk. We now have time for some questions. If people would like to ask questions, then please raise your hand or pop the question in the Q&A. I suppose just to kick things off, Erhan, I was wondering, when you calibrate your different agents, how stable do you think that calibration is over time? Given you can get the data, do you actually see variation in the dynamics of the agent parameters?
Not too much. So, for example, we were able to even in what I showed you, right? So we calibrated those parameters, and then we ran them for a day, right? And I looked at the real pool rate, and we were still close to the real pool rate. The Wasserstein time distance only changed from 4.3 to 4.4. So, I mean, this already itself suggests that the parameters don't vary that much.
I suppose I meant over sort of over months, sort of
Right. So
period.
I mean, it
Do you think the
depends. So
distribution of agents is homogeneous through time?
probably this changes, right? So the capital, we calibrated capital, but the risk aversion, right, and the delta, right? So these are of course changing through time, right? So for example, currently people are like the crypto prices are falling down, right? So versus they were going up. So these characteristics change, for example. Risk aversion probably will change over time depending on how volatile thing is. So that, over a long period of time, this should change. But over a short period of time, they look very stable.
Mm-hmm. Any other questions? Maxim, please. I've allowed you to unmute, Maxim.
Yeah, thank you. Thanks so much. Thank you, Erhan. Very fascinating talk. I had a quick question. Is this your assumption that that the pools are kind of one-sided, or is it true in reality?
No, they're not one-sided. You can trade in both directions.
No. The pool, the pools, the LP pools.
What do you mean one-sided?
That you contribute to A only to the left and then contribute to B only to the right.
No, but this is I mean, it's how the pool works, right? So it's not my assumption. This is how the pool operates.
Okay. Thank you.
So I suppose for me, I've not been keeping up with the variants of Uniswap. What is V4's main selling point?
I think there is more flexibility in so here, for example, you can be concentrated, but you cannot contribute to any tick, right? Just so you cannot just take, I'm just going to contribute to the one and two, or like you can do this, I guess, but I count to one and two and then 5 and 6. So you cannot do this in Uniswap version 3. But now you can do this. I mean, you would have to open a new trade. So you could do this, but you would have to like come twice to the market as different liquidity providers, right? Whereas now you can do, there is more flexibility, basically.
Benjamin Varian, please. You can unmute yourself.
Yeah. Maybe this is a very naive question, but I was wondering, considering the just-in-time attacks, have you tried to study it on tokens that maybe have less liquidity in the liquidity pools and that might be more subject to just-in-time attacks?
We did not. We only looked at this very liquid pool. That's a good question. I think it might be worth studying this.